In a matter of weeks, an artificial intelligence pipeline analyzed years of archival telescope data, validating over 100 hidden exoplanets human astronomers overlooked. The data was gathered by NASA's Transiting Exoplanet Survey Satellite, or TESS. Its mission is to monitor millions of stars, looking for the tiny rhythmic dips in brightness caused by a planet passing, or transiting, in front of its sun. TESS was remarkably efficient, flagging thousands of potential planetary candidates across the entire sky. But this success created a massive data deluge, resulting in a volume of signals that far exceeded the capacity of human review teams. The speed of discovery in modern astronomy is now limited by the human brain's ability to interpret this incoming stream of information. A dip in starlight is a promising lead, but it isn't a guarantee. The universe is crowded with astrophysical events that can mimic the signature of a world. This diagram compares a solitary planet transit on the left with an eclipsing binary star system on the right. Two stars blocking each other can create a light dip identical to a planet's shadow, so researchers often can't tell them apart on a graph. Separating these imposters requires expensive, manual follow-up observations with ground telescopes, a process that takes significant time and funding for every single candidate. As a result, thousands of potential worlds remain unconfirmed on hard drives, waiting for a method that can distinguish a real planet from a stellar lookalike. At the University of Warwick, researchers developed RAVEN, the Ranking and Validation of Exoplanets pipeline, to automate this entire detective process. To learn how to spot a fake, RAVEN couldn't just study known planets. It had to be trained on the exact geometry of every possible false signal. The team generated hundreds of thousands of realistically simulated fake planets and false positives, injecting them directly into actual, noisy TESS light curves. RAVEN even accounts for nearby false positives. As shown here, light from an adjacent star often bleeds into the target star's pixel on the telescope sensor, creating a diluted dip that looks like a small planet. By training on this massive catalog of synthetic fakes, the AI learned to recognize the subtle patterns that reveal an imposter. When RAVEN scans a new signal, it pits the planet hypothesis in a strict face-off against 8 different false positive scenarios. The first half of the system uses a gradient-boosted decision tree. It employs a series of sequential trees where each new model corrects the specific errors made by the one before it. This process allows the model to minimize the loss function and tighten its accuracy with every round of analysis. The second half of the brain is a Gaussian process classifier, which calculates a mathematical probability for the candidate amidst the background noise of the data. For a planet to be validated, the signal must achieve a probability higher than 99% against every single false positive scenario. This automated gauntlet removes the subjectivity of human review, providing a consistent, mathematically grounded verdict for every star in the mission's archive. The results were immediate. RAVEN validated 118 new exoplanets and identified more than 2,000 high-quality candidates that had never been formally confirmed. The haul included extreme worlds, like ultra-short-period planets that complete an entire orbit around their stars in less than 24 hours. By providing a precise count of the planets in this region, RAVEN confirmed that Neptunian desert worlds, Neptune-sized planets orbiting very close to their stars, are extraordinarily rare, occurring around only 0.08% of Sun-like stars. Having such a clean, well-characterized sample allows astronomers to move beyond finding individual worlds and start measuring the large-scale trends of planet formation. While short-period extreme worlds are easier for TESS to find, the ultimate goal of the mission is the search for small, rocky planets, worlds that resemble our own. The RAVEN search successfully isolated 18 potentially terrestrial, Earth-sized candidates orbiting particularly bright stars. Because these stars are so bright, these candidates are now prime targets for the James Webb Space Telescope to scan for atmospheres and potential biosignatures. The data suggests that approximately 10% of all stars like our Sun host a planet on a close-in orbit. If one automated search can pull over 100 worlds from existing data in weeks, the catalog of our solar neighborhood is just beginning to expand. The signals were always in the data. We just needed a pipeline fast enough to confirm them. Subscribe to see what James Webb finds on these